Welcome back to the deep dive. Today, we are focusing on, well, one of the highest stakes applications of deep learning, medical image classification. Think about the task a computer vision model faces, identifying, say, a tiny ambiguous tumor, or maybe a subtle hairline fracture, or even a rare abnormality hidden within just massive amounts of visual data. It's really hard work. And when the stakes involve diagnosis, well, the model just can't afford to be wrong.
And that's exactly where the rubber meets the road. While the technology, CNNs, convolutional neural networks, is powerful, deploying it in specialized fields like oncology or radiology hits two major practical roadblocks. These make it uniquely difficult.
Okay, roadblock number one being the data itself, I imagine. We need doctors, actual experts, to manually confirm and label thousands of images, saying, yes, this is definitively a grade 3 glioma. And that process is notoriously slow and expensive, meaning high-quality, fully annotated samples are pretty scarce.
Precisely.
Yeah.
Really scarce. And while we often try to skirt that by using transfer learning, taking a massive model trained on general images and fine-tuning it, that brings us right to roadblock number 2. Transfer learning's benefits kind of fade. They diminish significantly when your medical dataset suffers from irregular distribution between classes. This is the core problem we're tackling today.
Okay, let's nail down what that irregularity looks like in practice for you, the listener.
Think of it this way. Say, in a study focused on a rare disease, maybe 99% of your samples are common, benign tissue, and only a tiny 1% might be that extremely rare aggressive tumor type. Your model, well, naturally, it learns to kind of ignore that tiny, difficult 1%, because statistically, the easiest way to optimize its performance is just predict benign almost every time. This inherent class imbalance introduces massive potential bias.
Right. So we have small data sets, and they are biased towards the most common case. It learns the easy route. Our mission today, then, is to dive into the CURVETE model, that's curriculum learning and progressive self-supervised training. It's a novel solution designed specifically to overcome these irregularity challenges and enhance generalizability when data is sparse.
Yeah, what's truly, I think, ingenious about CURVETE is that it doesn't just try to, add more data. It learns smarter. It combines 3 technical powerhouses, self-supervised learning, or SSL, to learn features without needing labels, then a unique class decomposition approach to manage that imbalance. And it integrates a really radical anti-curriculum learning strategy to guide the training process.
Okay, let's unpack this starting with the foundation. We still have that initial problem, limited labeled data. CURVETE uses self-supervised learning SSL. How does it build that foundational knowledge before it ever sees, a single labeled tumor?
Right. The SSL pipeline is the first crucial step. The model first learns general feature representations from a large collection of generic, unlabeled samples. We call this the pretext task. The model essentially teaches itself about structure, texture, relationships within images, general visual understanding. That learned intelligence, that base knowledge, is then transferred to the actual medical problem. That's the downstream task. And that's where those precious few labeled examples finally come into play for fine-tuning.
Okay, that sets the stage. Now, the real breakthrough you mentioned for dealing with the dataset irregularity is class decomposition. You said this is where the model stops seeing blurry, huge class boundaries and starts manufacturing fine-grained detail. How does that work mechanically?
Yeah, class decomposition is essential because it simplifies the complex geometry of the data distribution. It's quite clever. Instead of struggling with a single messy class boundary, we break the original class into simpler, more manageable subclasses. We start this process by extracting deep local features from the unlabeled images using a convolutional autoencoder, CAE.
Hold on, let's make sure we've properly anchored the role of the CAE first. Why an autoencoder specifically? What's it doing there?
Good question. The CAE is critical because it acts as a smart compressor and feature encoder. It takes the image, compresses it down to its most meaningful mathematical representation, the core features, and then it tries to reconstruct the original image from that compressed version. By forcing the network to compress and reconstruct, we ensure that the features it extracts are highly representative and also low-dimensional, which makes them perfect building blocks for the next stage.
Okay, so the CAE gives us these highly detailed, efficient feature vectors. Then to decompose the class structure, those features are clustered. Is that right?
Exactly. Those features are then clustered using the k-means clustering algorithm. This automatically partitions the features into groups, and each group is assigned what we call a pseudo-label. The parameter k, the number of clusters, controls the level of granularity. So how many distinct subclasses we fracture the original class into? Think of it like taking a massive blowy political map that's the original messy class and digitally breaking it down into dozens of tiny distinct neighborhoods. It forces the model to learn the specific streets, if you will, not just the generalized county lines.
I understand. So if we choose a high granularity, say K-4 we generate several structured datasets. We start with G4 where every original class is split into 4 distinct fine-grained subclusters. And this decomposition is what creates a progression of data from highly specific to highly generalized.
That's the necessary raw material, yes. You've now basically manufactured the specialized examples you need to train your model effectively, even without tons of labeled data. Now, the question is, how do we sequence the lessons? That's where the curriculum learning part comes in. And this is where CURVETE gets counterintuitive.
Right, because when I hear curriculum, my brain defaults to the traditional human learning model. Start simple, then get complex, like addition before algebra, then calculus. But CURVETE adopts the anti-curriculum learning anti-CL strategy, hard to easy.
That's right. It completely flips the textbook method on its head. If traditional CL goes from simple to complex, anti-CL deliberately starts with the most difficult examples and gradually progresses to the simpler ones.
Wait, hang on. Isn't starting with the hardest, most nuanced data risking overwhelming or confusing the model right out of the gate? Why does hard to easy work when easy to hard is the tried and true method for us humans?
It seems like an inversion, definitely. But it works precisely because of the initial data imbalance problem we talked about. If you start with the easy generalized classes like G$1, the original broad classes, the network quickly finds a comfortable local minimum. Basically, it learns just enough to classify the majority, easy cases, and then it kind of stops paying attention to the hard, rare details. It gets lazy in a sense.
Ah, I see. So by starting hard, you force it out of that complacency.
Precisely. If we connect this back to the decomposition we just discussed, the hardest examples are those defined by the highest granularity level, GK dollars. Training begins at GK dollars, where the differences between the subclasses are incredibly fine-grained, really difficult to distinguish. This forces the model to immediately learn highly specific, robust features, things like texture, specific cell shapes, subtle margins, features that are absolutely necessary to classify those small, hard subclusters.
Okay, I like the analogy you used earlier. Think of training a specialist doctor. We're not starting them with the common cold, which would be G-Della level. We're throwing them immediately into the rarest differential diagnoses, the G-Della level. If they can solve that high granularity problem, the common cases become almost trivial refinements later on.
That's a perfect analogy, yes. The trained weights, that hard-won specific knowledge gained at the G-Dollar level, are then gradually transferred to the next lower granularity levels, like GK1. At these levels, the features become more generalized. The training sort of refines itself, moving down the ladder until it reaches G$1, which represents the original broad class structure. This hard start progression encourages the model to fully explore a broader solution space, preventing it from getting stuck on easy solutions defined only by the majority class.
And this strategic use of the anti-CL decomposition happens in both phases we discussed, both the self-supervised pretext task and the final labeled downstream fine-tuning.
It does, yes. It's an integrated strategy used throughout the entire learning lifecycle.
So it's really doubling down on that hard-to-easy idea.
It is. And this doubling down, using the manufactured high granularity data first, is what really simplifies these complex dataset structures. And that's what delivers significantly improved classification, especially when data is highly limited and imbalanced.
Okay, so let's talk bottom line. What does this superior training strategy mean for real-world medical diagnosis? Let's look at the actual performance boost from the experiments. You mentioned they used actual patient data.
Yes, CURVETE was rigorously tested on 3 distinct, challenging medical datasets: brain tumor images, digital knee X-ray images, and Mini-DDSM, which are digital mammograms. And the comparison was against traditional transfer learning and also other progressive methods out there.
Okay, before we hit the specific numbers for CURVETE, let's quickly touch on that failure mode we discussed earlier. The ablation study, the comparison tests. Why did traditional transfer learning perform so poorly? Did it confirm your hypothesis?
It absolutely did. It confirmed our initial hypothesis quite strongly. Traditional transfer learning consistently achieved the lowest performance across all the datasets we tested. Why? Well, because the standard optimization process, without this kind of decomposition or a guiding curriculum like anti-CL, it naturally optimizes for the easiest majority class. If 99% of your data is benign, the model learns excellent features for benign tissue, but it effectively ignores the features critical for that 1% rare tumor. And that results in high bias and low generalizability for the hard cases that often matter most.
Right, which makes the achievement of CURVETE even more compelling then. So give us the performance metrics that really jump out. What were the results?
Okay, so using the ResNet 50 baseline model on the brain tumor dataset, CURVETE achieved an accuracy of 96.62%. And critically, that's a significant jump, about 2.6%, over the version of the model that used our sample decomposition strategy, but without the anti-curriculum learning component. So just having the decomposed data wasn't enough. The ability to structure the lessons from hard to easy makes a clear, quantifiable difference.
Wow, yeah, a 2.6% gain is actually huge in a clinical environment where every bit of accuracy counts. What about the orthopedic data? The knee x-rays?
On the digital knee X-ray dataset, this time using the DenseNet 121 baseline, CURVETE achieved 80.36% accuracy. And this substantially outperformed a previous state-of-the-art progressive model, known as CLIOG-CD, by more than 9%. That's a really big improvement. Across all the comparisons we ran, the results were statistically robust.
Statistical robustness is key, of course. Can you just briefly explain what that means for the listener? Why does that matter?
Sure. It means that the superior performance demonstrated by CURVETE, whether it was that 2.6% gain on tumors or the 9% gain on knee x-rays, it wasn't just luck or a fluke or some random chance variation of the data. The statistical test confirmed that the difference is robust and repeatable, with all the p-values coming in comfortably below the standard 0.05 threshold. Basically, you can trust that this strategy actually enhances the model's ability to generalize and perform well on new, unseen images.
So it's a clean sweep, really. It confirms that intelligently structuring the data presentation, specifically, starting with those messy, highly granular subclasses, is the key. That's what unlocks robust feature learning when high accuracy on rare classes is absolutely non-negotiable.
It powerfully confirms that anti-CL combined with decomposition is a generalized solution, yes. By forcing the network to tackle the hardest, most specific features first, it ensures the network builds representations capable of handling nuance, which is vital for improving feature transferability and generalization in these tricky, limited, irregular data environments.
So the core takeaway for you, the listener, is that CURVETE provides a really promising new paradigm for medical image classification. It doesn't rely on somehow finding more labeled data, which is often impossible,
Right.
but rather on intelligently structuring the learning process itself, moving from complex, high granularity features down to simple, low granularity features, specifically engineered to handle the reality of data irregularities.
hmm And by addressing the challenge of imbalanced data head-on with a strategy that actually encourages feature diversity, it ensures that even the rarest, most complex diagnostic features are learned and retained. And that should translate directly to higher clinical accuracy down the line.
Which raises a really important kind of forward-looking question for you to consider. Given that this anti-CL strategy forces the model to learn the most detailed, specific features first, those high granularity patterns, how might this hard start approach fundamentally change the way we structure training for other complex, nuanced fields? Fields outside of medical imaging where fine-grained detail is critical. Think about, say, identifying subtle signs of equipment failure in complex manufacturing plants, maybe spotting minor yet crucial environmental shifts in climate data. The potential for this hard-to-easy learning to solve other needle-in-a-haystack problems seems, well, potentially enormous, something to mull over.